example 3. So this is a 3-dimensional complicated case. Okay, a short rectangular post supports compressive loads of P, Q, R, 3 forces, as shown in the figure. A top view of the post showing the locations where P, Q, and R are applied to the top of the post is shown in this figure too. And determine the normal and shear stresses at point H. Okay, you can see that the point H is here. So if you cut a cross section, well, you will get a YZ plane, right? So this is the left figure is a top view, so it can also serve as a cross section. So it will be a YZ plane. Okay, the Y is here, and the Z is here, right? So we will redraw this. We will redraw this cross section. Then we'll do more analysis. Okay, let's draw it here. So you will get a y-axis, z-axis here. Right. So your point Q, the force Q is applied here. It's pointing down. It's pointing down, right? So it will have a distance to the z-axis, that is E3. Okay, this is E3. And this is the load Q. And our load P is here, also pointing down, right? And it has a distance to the y-axis, it's E2. And its distance to the z-axis is E1. And we have the third loading by R. Where is R? The third loading R is here. Okay, here is a B, and here is the H. Okay, so this is the sketch of the cross section. Now we can do further analysis based on this cross section. Of course, the point, our target point H. Point H is here. Okay. Then our first step is to cut an YZ plane at point H, like what we have just done, and then analyze the internal forces. Okay. Let's analyze the internal forces. So here we have 3 forces, so we need a bigger table, right? Use a bigger table to analyze all possibilities. So here you have 3 forces. Those are the external forces. You have Q in Kn, and P in Kn, and R in Kn. And let's sum them in the end. Okay, but here we'll use Newton, since we'll use Newton millimeter in calculations. Okay, and then we can see what internal forces we can have. Okay, we will have a F, the axial force, the normal force. The normal force will be along x direction, Fx. And if it's along y and z directions, then we will call them shear force, right? So we use Vy and Vz to denote forces along y and z directions. How about the moment? Well, if you have a bending, you have a moment about x, about the normal direction, about x direction, then it will be a torque, right? So it's not a bending moment. If this moment is about x-axis, then it will be a torque, right? Not bending moment, right? So we call it Tx. And if it's about y-axis, then we call it My. If it's about z direction, we call it Mz. Okay. We just have 6 potential components of internal forces. Okay. Then let's look at the first external loading, Q. Okay, the Q is right here, and on the YZ plane, it's pointing down. Then let's look at the Q. Will the Q make Fx? Yes, right? So it's right along the x direction. So it will be negative 18, right? Q is negative 18. So it's pointing down, compression, right? Negative 18. Will it have y components? No, so no y. Since it's along x direction, so no yz components. How about tau x? Will it contribute to tau x? No, it's 0, right? Since it's parallel to x. Will it make my? Will it make my? Look at the Q. The Q is right on y-axis, right? So this is at 0. How about mz? Will it generate mz? So will it generate a bending moment with respect to the z-axis? Yes, right? So the value will be QE3, the distance from it to the z-axis will be E3, the arm, right? So here you will have Q times E3. Right, so that would be 18 times 55. E3 is 55, okay? Then let's look at P. Well, does P make Fx? Yeah, P is right along x direction, so it will have negative, again, negative 34 here, right? The P is 34 kilonewton, negative in compression. Will it make a Vy along y direction? So the same as Q, right? It's right along x direction, so no yz components. So how about Tx? No, 0, right? Since it's also parallel to x. Then how about my? My is not on y-axis, right? It has the arm that is E2, right? So here you will have my components. The P will have a my component that is P times E2. Or 34 times 45. E2 is 45. Okay. Then how about mz? Okay, look at here. With respect to z-axis, the arm will be E1. Okay, so the P E1, or 34 times 70. Then let's examine R. Okay, the R is here, right on the bottom. Then will it generate Fx along x direction? So no, it's along z direction. It's along y direction, right? R is along y direction, so nothing on x. But it will be on y-axis, right? So along negative y-axis, negative 22. Along z direction has nothing. How about Tx? No, 0, right? It's not parallel to x, but the arm is arm is 0. Okay, so nothing. So about my, it's along y direction, right? So nothing my, so 0. mz, we have mz, right? The r, look at the r here. The r is here, right? So it has a distance, right, to the cross section. It has a distance of d, right? This is the distance d. Right? Although it doesn't look like has a arm on the cross section, but it does has a arm d, right? So this means that you will have a mz components, that is r times d. Right, so here would be 22 times 200. So then we can sum them. Okay, so here the fx, the sum of fx will be negative 52,000 Newton, right? The sum of Vy will be negative 22,000 Newton. And here will be 0, 0. And My will be just 1. You have only one component, right? 34 times 45. So we can set this is a positive thing, since it will, let's look at the PE2. Okay, the PE2 will tend to make a tension. PE2 will tend to make a tension at point H, right? So we can say this is a positive bending moment. Okay, we said this is positive. Okay, so here the results will be 1.53 million Newton millimeter. Okay. Then the mz will be complicated since it has 3 components. So we need to examine if are they having the same signs. Okay, just use the rule we just set for My. If the bending moment make tensile stress at point H, then we will set it's a positive bending moment. Otherwise, it will be negative bending moment. Okay. Then look at Q. Okay, the Q will tend to make tension or compression at point H. It will make tension, right? So this is a positive. And so let's use a different color. Okay, positive. The P will tend to make tension when respect to Y, but will make compression with respect to Z, right? Since we're talking about Z, right, you will have a negative sign to it. And R, the R, you need to look at here, okay? The R will tend to make tension or compression to point H. Tension, right? So it's a positive again. So here you can just add these 3 things together, considering their signs. Then you will get a positive 3.01 million Newton millimeter. Okay. So let me set the rules here. So the rules we used here to determine negative or positive bending moment is that positive means it makes tension at point H. This is the rule we set here to determine the sign of the bending moment. Okay, so we're done with the step 1. Then we can start to analyze the normal stresses at point H. Okay, the second step, normal stresses at H. Okay, the first component, okay, just look at this table again. So which components, we have 6 components, so which ones of them can make normal stress at point H? Fx can, right? My can, and Mz can, right? So we'll have 3 components to determine. Okay, the first one is due to Fx. Due to Fx, the sigma 1 just equals F over A, right? The F is negative 52,000 over the A. The A is 180 times 140. This is 180, 140, okay? There's 2 dimensions. That B. B is 140, H is 180. 140, 180. Okay, so here the result will be negative 2.06 MPa. Okay, so this is the first component. Then let's look at the second components due to My. So here we need to use the sigma equals mc over Iy, right? Use this thing. So we'll just sigma 2 equals my times c over Iy. Okay, the my has been determined. My there is a 1.53 1.53 million times the C, Y here, so the C at point H will be half B, right? Half B, the B is 140, so half B will be 140 over 2 over Iy. So then what is Iy? Okay. Look at the cross section. We need to determine Iy. It's either BH cube or HB cube over 12, right? So which one? BH cube or HB cube? HB cube. So we're talking about Iy with respect to y-axis, right? So you will have HB cube over 12. So 180 times 140 cube over 12. You have 41.16 million mm to the fourth. Okay, this is substituted here. 41.16 million. Okay, so you will get 2.6 MPa. And then similarly, the third component is due to Mz. Okay, the third component of it will be Mz times C over Iz. So what is Iz? Look at the cross section again. if the bending moment is with respect to z-axis, then the I will be bh cubed over 12, right? bh cubed over 12. 140 times 180 cubed over 12. It would be 68.04 million. Okay, so here the MZ is 3.01. $3.01 million times the C value will be half of H, right? It's 180 over 2. Over 62.04 million. Oh, 68, sorry. It will be 68.04 million. So the result will be 3.98 MPa. Okay, so here you can summarize them, just add them together. As you have three components. So the normal stress at point H will be sigma 1 plus sigma 2 plus sigma 3. Okay, the first is a negative 2.06 plus 2.6 plus 3.98. Okay, so here we get 4.52 MPa. Then the next step will be shear stress. Okay, so shear stress, we just do tau equals VQ over IT. Just look at which one will make, which shear force we have. Okay, how many shear force components we have? We have only one, okay? We have only one that is here, and you have a Vy. You have only a Vy, that is only shear force, okay? The Vy along y direction, right? If you cut an area through point H, okay, let's use a green color to cut it. Cut it through point H, what do you get? You get nothing, okay? So A equals 0. A equals 0, Q equals 0. So what is the tau? Tau equals 0. Okay, so nothing, so no shear stress at all. Then how about if the H is not on this corner, if the H is right here? So you should know how to calculate it, okay? You should know how to calculate the shear stress at this point H. You just cut it through the point and get area, a local centroid, global centroid, determine a D, etc. Then do the calculations. Okay?